Hi everyone, this is Calculus section 1.5 video number 2. So we went over these properties yesterday, or in the other video, sorry, it was yesterday for me. Did these two examples, so let's finish up 1.5. So these are solved, and these are going to be solving using the properties. Mostly, this A, when you have natural log, or log, with an equal sign in the middle, if you just think about it intuitively, if log of all of this equals log of all of that, then this must equal that. Now this is only when you have an equal sign in the middle. So let me just put down another example here. If I had this, log base 2 of x equals log base 2 of whatever, 17. Log base 2, so same bases on both sides of an equal sign, then x must equal 17. Alright, so then here we just want, it says solve, so that means I need to solve for x, so I just want to get x alone, so I'm going to add 1 to both sides. I get 2x equals 17, or x equals 17 over 2. Okay, this one I've already written in there. I have a log, same base, because they're both natural logs. Natural log of 56 minus natural log of x. So that is quotient rule. So what we need to do when we're solving these, where we have two logs, we need to combine them into a single log. So you're often using these rules in this direction. Two logs combine into a single log. Two logs combine into a single log. And the way I'm going to combine this is it's going to become natural log of 56 divided by x equals 4. So using the quotient rule. Okay, so then I want to convert this into an exponential. Remember, this has that invisible base e. So this is going to become e to the 4th equals 56 over x. E to the 4th is just a number, so this you can punch into your calculator. If I'm solving for x here, I would want to get this x out of the denominator, so I would multiply both sides by x. X divided by x is 1, so I'd have x times e to the 4th equals 56. Divide both sides by e to the 4th. So I have x equals e to the 4th divided by 56. I'll let you just put that in your calculator and figure out what that is. For my notes, I'm just going to leave it like that. And then this one I already wrote in there is the product rule. I suggest you write that in. So here I once again have two logs on this side of the equal sign, so I want to combine those into a single log. So that's the product rule. So log of this plus log of that becomes log of this times that. So this is going to simplify into this. Log of x plus 4 times x equals natural log of 12. Sorry, I should have said natural log there. Now right here I want to point out a difference in these two problems. This one I had natural log on the left, plain old number on the right, so I had to convert it into an exponential. Here I have natural log on both sides again. So that's similar to this example A that we had. So that means I can ignore the natural logs and just say x plus 4 times x must equal 12. And then I want to multiply this out. This is distributive property, right? So I'm going to get x squared plus 4x equals 12. This is a quadratic. So to solve a quadratic, I want to get everything on one side of the equal sign. And then factor, or use quadratic formula. I'm looking at this though, and I think it's factorable. I think it factors into x plus 6 and x minus 2. X squared, negative 2x plus 6x, 4x, negative 12. Yes, so this is either x equals negative 6 or x equals 2. Remember, for a quadratic, you sometimes can have an extraneous answer, one that doesn't work. So I want to check both of these answers. I want to plug them into my original equation and see if they work. And if you do that, you're going to find that x equals -6 is extraneous solution. So that is not a solution. So our only answer is going to be x equals 2. Do that though. I'm not going to take the time to do it in this video, but check that that is indeed true. All right, change of base. So when you have, remember your calculator, if you have just, oh, my camera's being weird here. If you just have plain log, that is log base 10. So the log button on your calculator is log base 10. There's your natural log. There's your e to the x. Okay? If you have another log base and you need to do math on it, you want to change it into a base 10 or into a natural log. So this is what you do. This is how I remember this. See how this x looks like it's over this a? So the log of x goes over the log of a. So this is, we've just chosen to convert it into a natural log. You could convert it into a log base 10. In that case, you'd have log x over log a. But in calculus, we use natural log a lot. So if you want to change a base, that's not a bad way to do it, to convert it into a natural log. You also, I don't think the 83 does this, but you can do this change of base on the 84 automatically, and you want to do the math button, and you want to go all the way down to, see this, log base, put that in, and then you can choose any base for your log. So you could choose e, oops, guess you'd make that 1 then, and then you could put x in, or whatever. You could make it any base. So that on an 84 or higher, you can use the math button to do a change of base. Okay, now this we're going to graph. So if you don't have an 84 or higher, you would change of base this into this, natural log of x over natural log of 2. Or if you have an 83 or an 84 or higher, just go to your y equals, and now you want to hit that math button. And you want to go all the way down to that menu item A, enter that, and then you're just going to put in 2 of x, and then you're going to graph it. Okay, you get that. It's zoomed out a little bit, so I like to go to my table, get some coordinate points there. Let me go up to 1, -1. Oh, now you'll notice anything negative is an error. So the domain of this is x is always positive. Even x equals 0 is an error. So at 1, we have 0. So if x is 1, we have 0. At x equals 2, we have 1. At x equals 3, we have 1.5. At x equals 4, we have 2. At x equals 5, we have 2.3. This is what we're doing. And then it keeps going up. And then I want to show you, well, what happens here is we approach x equals 0, but we never reach it. So x equals 0 is a vertical asymptote. So while we're looking at this, let's do domain and range also as this. Well, for domain, you can see our graph is only on the right side of the coordinate grid here, where the x's are positive. You can also see that in your table, because when the x's are negative, we have error. So this means x must always be positive. So x such that x is greater than 0, not even equal to. X approaches 0 but never reaches it. Okay, so that's our domain. And our range, if you think about y values, well, we have all these positive y values, and we have all these negative y values also. So it goes to the right, and then it keeps going up. So you have all these positive values. It keeps going down here, so you do have these negative y values, and they happen between 0 and 1. So when I look at my table, it looks like, oh, I don't have these negative y values, but all these other negative y values happen right in here between 0 and 1. Hard to imagine, I know, but that is what happens. So your range is going to be all real numbers. Okay, this last one is similar to what we did in 1-3, one of these exponential growth problems. So it says Sarah invests $1,000 in an account that earns this. Oh, this looks like my rate. I'm going to label that R. She invests $1,000. This looks like my initial amount, which we usually call P, stands for principal. Your initial amount compounded annually, so once a year. So this is not a PERT problem because it's not compounded continuously. How long will it take the account to reach this? So this is my final amount. That's my Y. Solve algebraically and confirm graphically. So this is a exponential growth problem. So I have my initial amount times 1 plus my rate divided by n. This is the number of periods that I'm compounding to the n times t. I'm only compounding once a year, so my n is going to be equal to 1. Okay, so P is 1,000, N is 1, R is 0.0525. Remember, you never do math on a percent, you only do math on a decimal. And Y is 2,500. So we're going to substitute all those into here. We're going to get 2,500 equals 1,000. 1 plus 0.0525 divided by 1 to the 1 times t. Oh, forgot to say t is what we're solving for because it said how long. So that means our time is our unknown. So it's an exponential because our variable is stuck up in the exponent. So the first thing we want to do is isolate the variable. So we want to divide both sides by 1,000. So I get 2.5 equals 1 plus 0.0525 to the t. Combine those. So that would be 1.0525 t. Okay, now variable is stuck up in the exponent. Do not want to do a common base on this. So I want to convert this to a log. Okay, so I'm going to have log, so this is an exponential with a base 1.0525. So I'm going to have log base 1.0525 of 2.5 equals t. So that's going to be my time. So this is the arrow method kind of in reverse. But the base of the exponential becomes the base of the log. So I'm going to do my change base formula here. So I'm going to do math, log base, and in this case, this is my base. 1.0525 of 2.5 equals 17.907. So t equals 17.907. So you could say this is 17.907 years, or approximately 18 years. Okay, now it says confirm graphically. So let's look back here and think, what do we want to graph? This is the function, actually this is the function we want to graph. And we want to find out when is y equal to 2,500. So So I'm just going to say what we want to put in our calculator is this function, 1,000, and I'm going to write this all simplified a little bit, 0.525 to the x. So we want to graph this and see when y is equal to 2,500. So let's put this in our calculator. Let's clear that one out. So this is 1,000, parenthesis, 1.0525, parenthesis, to the x. Okay, let's graph that. Should look like an exponential. I have a feeling this graph is not going to show. It's not going to show because my window is set for 10 and negative 10. So the graph is starting, my y-intercept is 1,000, so it's starting way up here. But I think that's okay. I'm just going to go to my table. And remember, I'm looking for when is the output at 2,500. So I'm going to go down until my y values, there we go. There we go. So this is, hope you can read this. This is 2386 and this is 2511. So you can see it happens between 17 and 18, which is exactly what we found when we did it algebraically, 17.9. So we solved it algebraically and we confirmed graphically that yes, that's true. If you wanted to change your window, I'm going to make my y max, let me make it 1,500, and then let me try graphing it and see if it shows up. There we go. Okay, that is it for 1.5. One more section in chapter 1, and then your big test.